Yeah, thank you. Sorry, Sara.
Yeah, no, I didn't say anything important so far. I just rewrote this lemma from yesterday. And this was something that I also asked you if you want to work a little bit in the tutorial session to focus on. So we have this, we will use that. Again, to warm up, I just give you two notations from graph theory. The first one is when I have a graph and I remove some vertices, let's say V1 to Vt. By this, I mean that in my graph G, there are some vertices V1 to Vt and some other vertices here. There are some edges between these other vertices, some edges between these vertices and some in between. And when I remove this set, it means that I'm really removing these vertices, all connections between themselves, and also all connections in between. Okay, so I'm removing the vertices, all edges adjacent with them. Okay, so for example, in this graph, when I remove this vertex, what I get is just this one. Okay. And the other notation is the notation of the neighborhood of a vertex in my graph. This denotes all the set of all vertices which are adjacent to a given vertex V. So if this is my V inside G, these vertices are the elements of this neighborhood set. Okay, so for example, these two yellow vertices are the neighbors of this white one. Okay, so we have these two notation just to be sure that everybody knows what I mean when I write them. Okay, and now I want to go to lemma 2. Again, I mentioned it somehow in our tutorial session yesterday. Let E be an edge AB.
Yes.
EG. Then, okay, IG second square free power AB. I mean, I told you yesterday that if I have the edge with vertices A and B, with endpoints A and B, I may write the monomial the same, just with the names of the vertices. And now we want to describe what is this actually. So if I want to show you in a picture, suppose this is our G, and we have this edge E with endpoints A and B. Okay, there are some edges around, and there are some edges here to the neighbors of A and B. And now we want to see which monomials are multiplied with AB, and the result is inside the second square free power by the definition of the column ideal, right? Okay, let's see. I mean, if I consider this something like this edge, which has no common point with my E, okay? So if I multiply this pink one with E, they make a matching, a two matching. right? So the result is a generator of IG squared. Agree? So it means that all such pink edges have this property. Yeah, but how I can describe them? They have no connection with E. It means that if I remove these two vertices, A and B, I mentioned what I mean. When I remove them, all edges adjacent with these two vertices are also disappeared, right? And then it means that I am looking at the graph G minus A and B. Do you agree? All pink edges are the edges of G minus A and B. So for the moment, we have some of their its generators for the moment. So all generators of the edge ideal of this graph have this desired property that we want. What else? Again, look at this picture. Now, look at the yellow edges, okay? And their endpoints other than A and B, these points. For example, if I denote this by C and denote this by D, okay? And if I multiply C and D to A and B, it is a square-free monomial because they are on 4 different vertices. But how I can see it as a 2 matching, C and D may not be connected. But we are in commutative ring, and I can rewrite it as E A and D B. Agree? Then it is clear to us that this is really a 2 matching, right? And then this is a generator again of this second square-free power. Yeah? So how I can describe this situation, these yellow points now, they come from the neighborhood of either A or B. Yeah. So then I will add this. I write it here as the ideal generated by all CDs such that C is in the neighborhood of A, D is in the neighborhood of B, and C is different from D, and they are not also A and B, just to be more precise. Okay? And you can later, maybe in tutorial session, check that that's all. So just to understand what is this column ideal is, you can divide it in these 2 scenarios and we are done. Okay? So are you happy with these 2 pink and yellow scenarios? Yeah? Okay, so then this will be my lemma 2. We will use that later. Louder a little bit.
Your notation, does the neighborhood include B?
No, no, it's not a closed neighborhood. It is open neighborhood. Okay, and then lemma 3. Okay, we described this ideal before going to lemma 3. Look at the generators here. Here you are clearly seeing an edge ideal of something, right? And here also you are seeing some square-free quadratic monomials. You can see this also as an edge ideal, right? So the whole thing, this guy, is really the edge ideal of some graph. the monomial, square free, quadratic. Let's call it H for the moment. And if we need, we can use that later. Okay, but this is important because then we can apply whatever we know about edge ideals on this column ideal. So it's nice enough for us. And now again, E as before is an edge. Then we want to say something about the regularity of this column ideal. Is less than or equal to mu G. Okay. This is lemma 3. I mean, it's technical. I don't want to go to the proof of this lemma, but I can at least start for those who want to continue later for themselves, just to practice a little bit. You can use induction.
This for only second power.
Only for second power, yes. For the upper bound, we said that maybe it's good to recall. For the upper bound that we made a question, we knew it for k equal to 1, very first power, and the very last one for nu g. This is the highest power that we have non-zero, yeah. And then in between, we did not discuss. Now we are discussing the second power, okay? So induction on number of vertices and you can start when for the case that G is just an edge because it has at least one edge. This is your base step. And then your second power colon E. I mean, the second power is already 0. Yeah, because you cannot find any 2 matching here. So then everything is trivial. And then you can assume that you have at least 2 edges. So this is the first step. The second step, at least 2 edges. And then you can argue in 2 cases. The first case is that the union of an A and an B is just A and B. It means that they are the only neighbors of each other. This is an easy case. And otherwise, they have other neighbors. So this is the technical part. If you can manage this one, then you are really done. But for this, I can recommend that look at H above. Right now, I told you that this column ideal is an edge ideal of something, then you can benefit from that edge. Yeah, but this is a very short, rough for the sketch, for those who want to work with this stuff. But for the moment, I just want to use this inequality. Okay. Yeah.
Which case this we have equality.
Here, so we don't need to check if we have equality here because it's just a colon ideal. But in lemma 1, the first part, there are some classical cases that we know that their equality happens. And since we use in this part that lemma, so you can have at least some cases that equality happens. But right now I don't have the classification. But if you use the complete version of that lemma, you will get cases that there is equality. But in general, we don't have any characterization. Okay, so this is lemma 3. Everything is okay, almost okay so far.
What is the surety that this IG is an anti-ideal of some law?
The IG is a edge ideal. Once more time, maybe I misunderstood you.
The first idea
Uh-huh.
is why
Here. Once more time, look at here. We deduce that this column ideal is this plus this. Yeah. And this is clearly edge ideal of the graph after removal of A and B, right? And here again, you are seeing some quadratic monomial, which is a square free because we said that they are different. So again, you have, I mean, whenever you have a square free monomial, which is quadratic, it is an edge ideal of something. You can describe this graph. I will ask you, I mean, to do it in tutorial session. Yeah. Okay. And now comes lemma 4. Okay, we have an edge ideal. So it means that it is generated by some monomials corresponding to some edges. I write now simply edges just to simplify the notation. Then for any I, we have IG squared free, of course, E1 to EI, column EI is, I think it's better to write it here. Okay. Let's see. Let us discuss this a little bit. Okay. I minus 1. So these are the edges of my graph and generators of my edge ID, right? E1 to EI minus 1 are here and column EI. So let us see if these edges, any of these edges have a common vertex with EI, for sure they are distinct. So they can share at most one vertex, right? So if they share some vertex, suppose this is EJ among them, and this is EI, right? Okay, now I want to see what should be multiplied with EI so that we come to this ideal. Something here divides my monomial. So if I just multiply this vertex to my EI, yeah, then what happens? What the EJ here, this is something in between, divides the monomial, right? So I suppose this is A, B, C.
So
Yeah.
all those vertices which are appearing in the support of EI, each for j is equal to 1 to I minus 1.
Those who share a vertex with this. This endpoint of those edges which share a vertex with my EI comes here. Yeah. So here, I mean, I have EI equal to BC, right? If I multiply A with EI, I get ABC, right? And EJ, which was AB, divides this AEI ABC. Yeah. So it means that this A belongs to this column idea. So, I mean, roughly speaking, I just put them here some variables that you know. Okay, so you know which variables are there now. Okay, and this is a good picture for this. What else? If some of these edges do not share any vertex with this EI, it means that I am in this situation. This is my EI, let's say B, C, and this is my EJ, A, B. Yeah? So it means that this EJ is already a generator of the second power colon EI, right? Because when you multiply this this EJ to EI, you get the monomial AD, BC, which is a 2 matching, and this is a generator of this second power, right? So then I just need to add IG second square free power colon EI, right?
Get the expression from the lemma.
Hmm?
And we get the later expression from the lemma. I second power.
I use this for what? I didn't get your question.
Asking that can we, so you can get.
Now we want to use lemma 2 for this expression for sure. Yeah. And we want somehow to get rid of these variables with the second part of lemma 1. We want to combine these things to get something. Yeah. Okay. So I'm done with my bunch of lemmata. And now I just want to recall what was our upper bound and what we were looking for in the last session. So are almost clear what yeah.
Is there a way to make it a little bit more precise what the first bunch of variables are?
Yes. Here, okay. Some of these edges are sharing a vertex with this EI. Okay. So suppose this is EI and it is BC, and this is one of those EJs, E1 to EI minus 1 with these vertices. Okay. And now, okay, EI is just BC. And if I multiply it with this variable, AEI, which is ABC, okay? Then do you agree that AB divides ABC? Yeah, so it means that this is inside whatsoever I had with, in particular, EJ. Do you agree that this is here now? Because EJ is just AB. And a monomial belongs to a monomial ideal if it is divisible by one of the monomials inside. And this element is divisible by AB, which is EJ. So this is in this monomial ideal. It means that A is inside whatever we had, colon BC, which is EI. The colon ideal is defined in this way. all the things which are multiplied by this guy and lies in this guy, okay? And now you know that A has this property. A, B, C belongs to this ideal because it is divisible by one of the monomials inside here. And then by bunch of variables that I put there, I mean this. When they share a vertex, this other edge or vertex of EJs belong to the idea. Is it better?
Yeah, this part is okay. I just mean we can have a way to describe this full set of variables. A little bit more simply. I mean, I know that we can run through all these edges. And
Yes.
into Is there a way to write it formally?
Yeah, I mean, it's we need some notations actually. Yeah, I just wanted to get rid of that. I mean, we wrote it more precise in the paper, of course, but for here, I just need to have some to make sure that there are some variables. They are not dangerous for me because by the second part of lemma 1, now, I mean, immediately I will get rid of them. So I don't want to consider them anymore. So I don't want to go to details of their notation. Yeah, but of course, one can, you're right that it's better to have a better expression for them. Yeah. Okay, so maybe I remove this part. Okay. The upper bound that we discussed was this one, regularity of the kth square power of IG. It was a question that if it is in general for any k less than or equal to this guy, and I mentioned that you can write it, of course, as nu g plus k, but I preferred this one because for the ordinary power, our bound was this one, and then we could have a better feeling and better comparison with this. Okay, this was a question. We said that for k equal to 1 and nu g things were fine. We had this upper bound. We discussed it yesterday. And then we came to the case k equal to 2. And that's why you see in my lemmata mostly k equal to 2. And it means that our bound will be now nu g plus 2. So we would like to show that regularity of the second square free power is just bounded above by this number. Right? This was my goal. Okay. Now we can try to use our lemmata to prove this. As usual, we take our ideal to be generated by some edges, E1 to ER, the monomials corresponding to them. And first, let us observe something that the regularity of the second power E1 to EI minus 1 yeah, colon EI. Okay, is less than or equal to what? So this is the same as what you see in the left-hand side of lemma 4, right? Okay, but this was this summation of some variables and this column idea, right? Okay. And so for the moment, we are using lemma, what was the number? 4. And, okay, if we look at this, the right-hand side and go to lemma 1 part 2. Now I just want to disregard this variables part, but then I get an inequality, right? Of what? Of the column part. Do you agree? If I repeat that part, the second part of lemma 1, each time I get rid of one of the variables and I keep the inequality. And at the end, by lemma 1, 2 repeatedly, what I get here is regularity of Ig second power EI, right? Do you agree with this star observation? Yeah? Okay. Again, we want to use lemma 1, but this part 1. So I start with my goal. So we have regularity of the second square p power is less than or equal to, now I'm applying lemma 1, the first part, okay? It is less than or equal to the maximum of, okay, for that part, I need some monomial of certain degree. I'm now taking for this u to be E1, which is a which degree? What is the degree of E1? 2. So regularity of, okay, please compare what I'm writing with the first part of lemma 1, replacing u with E1 of degree 2. Regularity of, again, the second square, the second power and E1. For the moment, are you happy with what I wrote in comparison with lemma 1 part 1 u E1? Yeah? Good. Okay. Why did I write 2 here? Is the replacement for what in lemma 1? B. Yeah. Okay. And now I apply lemma 3. Look at lemma 3, please. Lemma 3, where is it? Gives an upper bound for this column ideal. Yeah. And now I'm seeing this column ideal here. So it is bounded above by nu g, right? So I can write now the maximum of, so I replace the whole part here by nu g plus 2 and the rest. Yeah. So this part is now replaced by lemma 3 with this nu g plus 2, and I just repeated the other item here. Okay, I want to keep this one as it is. Now I want to focus on this part. I would like to see this as a new ideal and apply lemma 1 part 1 again with a new u. Okay, so then lemma 1 part 1. This time I take u to be E2, which is again of degree 2. So then it's maximum of, I keep the first item. And now I apply lemma to this with u equal to E2. So just to be more precise, I prefer to see the notes. So I have IG squared E1 colon E2 plus 2 and regularity of IG squared and E1 and E2. So this yellow part is repeated here. This red part has been obtained from this red part by applying lemma 1, 1, u equal to 2. Agree? So this part is just repeated. You can see it as some ideal J. And then you're making the colon with your new element and also add this to your idea, right? Okay, and we can proceed in this way actually. Okay, maybe you take another look at our observation star. We said that for any I, if you have bunch of edges here and then colon another edge, the situation that we have here, one edge here, colon another edge here. Then you can compare with the regularity of this square free power and this new edge, right? So now I can write instead of this regularity, this one, because we are just comparing, so no worries about inequalities. So what I get here is less than or equal to the maximum of nu g plus 2. I'm repeating this one. And then the regularity of, what was that? IG squared colon E2 plus 2. And I repeat the third item as it is. So what is different from the above is this one. It is by star. Yeah? Agree? Okay, again, by lemma 3, I know about this. So again, this is less than or equal to nu g plus 2. So I can disregard it because I have it already here. So it is then less than or equal to maximum of nu g plus 2. The same, I don't rewrite it again. So and regularity of the rest. So this is by star, and this is again by lemma 3. Okay, and so on. I think now the procedure is clear to everybody. So you can proceed in this way. You will keep nu g plus 2 somehow in each step. And okay, in each step you are adding one new edge. So at the end, I have here IG second square free power E1 E R. Okay. This can be checked more precisely, can go one another step if you're doubting, if you're not relying on me in your tutorial session. Okay, but then let us look at this part. What was IG squared? It is generated by two matchings, right? But now I'm putting all edges here, right? So what does that mean? What is this ideal now? IG squared E1 to ER. Can you tell me what is this ideal now? I have IG squared, so all two matchings, and I add all edges themselves.
That's all. I don't want.
IG to the first power or IG, because I have all edges, and for sure all two edges, in particular all two matchings, are divided by these, so all are extra now. I don't want them. So what I can write here is that this is just the regularity of IG, and here we said that the bound is valid for k equal to 1. So k equal to 1 means that the regularity of IG itself is less than or equal to nu g plus 1, right? So this is less than or equal to nu g plus 1, but I have here nu g plus 2. So I can write this maximum as nu g plus 2, right? So we started with this guy. We came to this point, and this was our upper bound for k equal to 2. Yeah? You may try to, if you have some doubts, you can just check in between, maybe one more step, just to make sure how we are relating these lemmata and how we can deduce the point. Okay, so is that okay for the moment? Yeah. So I think I'm allowed to remove this part at least. Uh, let us recall our upper and lower bounds. For this specific power, for k equal to 2, yesterday we showed that, I mean, in general, our bound was, we were discussing was to k plus nu 1 of g minus k. What was nu 1? Nu is matching number, and nu 1 was what? What's this? Induced matching number, right? Okay, and if I put k equal to 1, k equal to 2, it becomes nu 1 plus 2, right? And here you see that what we obtained is nu g plus 2. Not always we have nu 1 equal to nu g. Of course, we have always this inequality, right? But in some cases, we have equality. And this is really something interesting in combinatorics. For those graphs that we have such an equality, those graphs are characterized and they have a very nice combinatorial characterization, and they called Cameron Walker graphs. You can see the characterization. I don't want to go to details here, but Takayuki Hibi has some papers on these this class of graphs, but they really come from combinatorics, their characterization. Okay, it means that if G is a Cameron-Walker graph, we can have an exact value for the regularity of the second square free power. I mean, we are obtaining bounds, but for sure we are more interested in having precise formulas, right? And now, at least for a nice class of graphs, we have the exact value for the regularity. Okay. Again, in tutorial session, those who do not want to think too much, you can read what are these graphs and what are their properties. Is it clear? Okay. I want to stop talking about regularity. In the remaining time, I would also like to give you a few words on other invariants, which are also interesting for people who are working in this direction. Okay, so you might know what is depth, and if not, it is the length of the maximal regular sequence that you can find, that's the sequence belong to the maximal graded ideal. Okay, or you can also read it from the resolution, because now we are familiar with resolutions. And if you take our object as polynomial ring I monomial ideal of our subject, then by the so-called Auslander-Buchsbaum formula, it is just n, the number of variables of my polynomial ring, minus the projective dimension. You know, projective dimension, it was the length of the minimal graded field resolution that we were talking about. And this number is depth. Okay, so this is one way of thinking of depth. For ordinary powers, there has been a long-standing question that people expected that the depth function in terms of k for ordinary powers is a non-increasing function. And there are several classes that people were successful in showing this, but at the end in 2014, I think, Kaiser and his co-authors, or her co-authors, I'm not sure, found a counterexample. So this is over in general for any square-free monomial ideal, but still this is open for edge ideals, that the depth function of the ordinary power is a non-increasing function. Okay, motivated by this, one can ask about the square free powers. What's the situation there? So for this purpose, for square free powers, I give you two notation. Let us call dk this number. The minimum degree of the generators, of the minimal generators of our monomial ideal, which is the kth square free power. So now I'm trying to be more general. I'm not just in the case of edge ideas. I'm talking because we started by definition of a square free power of any square free monomial ideal. So this is the situation. So we take and that ideal, the square free monomial that we are starting with is has not to be necessarily equigenerated. So it can have different degrees in its generators. So we call this minimum decay, and we define a function denoted by gi k for any meaningful k from 1 to nu I, which was defined in the first lecture, to be depth of my object minus dk minus 1. We can call it depth function, but we called it normalized depth function. When actually in the beginning we were looking at just depth part, but in our examples we saw that, okay, seems that this is, I mean, this new expression is non-negative. So we were more interested in this and we called it normalized depth function. So this is the first thing that you can think about. You can use this Auslander books, I mean, as a hint for those who want to try that if it is true or not. You can also use Auslander books one formula for this, combined with Huxter formula, and can almost easily get this point. And for those square free powers which whose normalized depth function is the minimum possible value, which is 0, we say that they have minimum depth function. And it is a nice problem to characterize all such a square free ideals. And even for graphs, this is not known for all edge ideals that which are obtaining this minimum value actually. So when we say minimum depths, we mean GIK equal to 0, just in short. And there are several classes of square free ideals for which we know that they are of minimum depths, their square free powers. I just write some words. I don't go to details, but this is just some keywords for those who want to search edge ideals of complete graphs, complete bipartite graphs, for those graphs whose complement is disconnected, for all metroidal ideals, I mean, outside the world of graphs, square free Veronese ideals. Don't worry if you don't know what they are. You can search for definitions in tutorial session or later. I just want to give you some classes, some nice classes that are interesting in algebra or combinatorics, just to tempt you to think about this characterization. Yeah, and so on. There are some other classes. I don't want to go to all classes. So but there was a conjecture by us. I mean, I should also mention that what I'm saying is based on, has been based on two joint works with Nursel Array, Jorgen Herzog, and Takayuki Hibi, and myself. So we had this conjecture that, as I started with, GIK, the normalized depth function, is non-increasing. And for several classes of ideals, we proved it and some other proved it. But recently, there's a very short note that claims that there is a counterexample. Neither of us have checked it, so I am not sure now if it is, because, and it's not published, it's a short note on arXiv. So now maybe this is not a conjecture anymore, but still interesting, because beside all classes that are proved, for them is proved that this is a non-increasing function. The computations also show that it is really the case, and one only counterexample exists. So still characterizing ideals which have non-increasing function or have minimum depths is interesting, no matter if it is a conjecture or not, very likely not. But it could be.
Type of,
Sorry?
for- type of, for example, for scale free.
Yeah, sure. It's for square feet. Yes. And yeah, and somehow it's the abstract says that the difference between G1 and G2 is really big. So they differ a lot. So I haven't read that note yet. Yeah, but I tried to give you some more compact and more precise list of research problems in the tutorial session. So I think it's better to stop here, and then I give you that list later. Thank you.
Is there any question or comment?
These are the recent
Sorry?
paper of the Saeedi kind of talk and so, many years or are there?
This is our paper. Both are published now. I mean, very recently, one of them, 2023 and 2022 maybe, or one.
Ideals, there are some example which does not have minimum depths.
Yes. Okay, we have okay, a part of the paper is devoted to ideals with linear quotients, and there we try to build a class of graphs, a kind of whiskered graph, so to say, and then we characterize for which construction how we can add these whiskers to get minimum depths, and for the rest, for sure, it is not the minimum. So it is really classified.
Exactly process. Later ideal of some graphs or
This is a square monomial idea.
yes, but it's still it's not that big.
No.
It's not.
Yeah.
And the last one, why do you consider this word very monomial ideal and then you consider case this word very covered and it's not a monomial ideal.
Then you're losing some generators from the very beginning somehow. What you are saying is true in some sense. I mean, there is some definition. I just wanted to mention it in my problem list. Okay, maybe I just shortly describe. I mean, very recently, Ficara and
Can you repeat the question and then answer?
sorry.
The question is still answered.
He's asking, if there is a situation, if one can define this kind of powers for non-square free monomials in the very beginning, okay? And a very recent paper by Ficara and Array, in that paper, they start with any monomial ideal. They don't call the power the square free power, but they call it matching, just to show that it is related to that one. And this is generated by those multiplication of the generators of the original ideal, which is a regular sequence. So the same definition, if you remember in the very first lecture, I defined it in this way, but we left it, okay? Because we were interested in a square free things and we didn't use this expression that much. And this is the first time that they are defining this for any monomial, but they don't call it a square free because this is not any, I mean, if you expect something a square free, this has not been considered, okay, which is the case, which can be the case. But very likely, I mean, it can be a very somehow not dense ideal. You don't have too many generators somehow. You will lose in the very beginning the generators. But the multiplication of those are which provide regular sequence, and these are coming from GI. Almost the same definition as my first definition. So this has been considered, but still very little is known about it. They try to define the normalized depth function. They try to look at the lower and upper bounds of regularity that I discussed here, but all are partially studied now. So this direction is now somehow not touched that much. Yeah, thanks for the question. You wanted to ask something?
Please provide the reference of the paper inside the classification of the graph.
Yes, I want to give you the references also in tutorial session, I think.
And second thing is that like put some light on the bridal ideas.
Sorry?
Bridal ideas. So
What?
Main problem like this.
The definition, I didn't.
She's asking for, can you write the definition?
Maybe not now, maybe in tutorial session, if you want, we can discuss, just meet, maybe now, over time, yeah?
Okay. Okay, is there any other question? No, so let's sign this.